first announcement is, I don't know if you're familiar with this, but the Edwards College, COFA, we have this program known as academic coaching. Faculty will come back to campus for dinner, and we'll hang out in Sino Grill, and you are welcome to attend and come and just talk to faculty, ask them questions about their class. If you're having, let's say you're in Poly 101, we have Poly 101 instructors, so you can come talk to them. I'm going to send out the email to the class about all of the dates that are available for the rest of the semester. Like I said, I've got that half written. I'll do that tomorrow. But for our class, I will be doing academic coaching on Monday the 9th, which is the week of the midterm, and again Monday the 13th, which at that one hopefully we'll talk a lot about your course papers. It's from 5:30 to 8:30. You don't have to be there the whole time, I do. And it's in Sino Grill, and dinner's on us. So you come in, you sign in, we'll give you a food voucher. You can go get $8 worth of whatever, and then come and eat dinner with me and ask me questions about the class. Our department has Poly 101, Poly 201, Poly 200, and 205 covered. So, and there'll be lots of other faculty from other departments in COFA, English, philosophy, history, comm, down on through the line. So you should hopefully hear more about this. The sessions will start next week. And any questions about this? You guys heard of this before? Well, good. I got one nod. I'll take that. All right. What I want to talk about today, I want to talk about measures of central tendency. So we're into chapter 3 now. And last class we talked about how we can measure data and the various formats we can put it in: ordinal, nominal, continuous, ratio, blah, 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 blah. We have a bunch of different ways we can take a concept and measure it and quantify it. What I want to talk about today are measures of central tendency. How can we take a very large data set and get it down to its essence? And for a measure of central tendency, what we're really talking about is like a single, skip that, a single statistic to describe the distribution. So as the book says, it identifies the center of a distribution of our data. Another way of thinking about a measure of central tendency, a single score that's the most typical, common, or frequently occurring. And today we're going to discuss how to calculate mean, median, and mode in the reverse order. There, okay? So, this is what? 6th, 7th grade math? Yeah? Something like that, right? You remember seeing this stuff before? We're going to add a wrinkle to it, though. All right? We got to make it like you're at university. And we're going to be thinking about this in terms of not just our data set. And literally, the homework will be like 6th grade homework. I'll give you 9 numbers and say, give me the median of this set of numbers. Flashbacks, right? All the way back to 6th grade. But for us, we need to understand this because of how it tells us the shape of our data. And that's when we're going to go back to this concept of a distribution of data. Now, distributions have essentially an infinite number of possible shapes. Because data itself make a little hand here. Data itself can come in all sorts of forms. The most commonly discussed forms of distributions, right? A frequency distribution. Frequency distribution tells us how often a value is found. The proportion or percent distribution tells us just that. Again, how often a value is found. We just, instead of taking the raw number, we just do it as a percentage. And a cumulative distribution, these are the sneaky ones. These are the ones that add up to your total. So whereas a frequency or one of these will look like a curve, a cumulative distribution function or a CDF will look like an S, because it goes from 0% to 100% along the range of values. Cumulative density function or cumulative distribution function. You always start at 0 and you always end up at 100%. We're not going to use CDFs in this class. CDF is like stat 310. We're not going there in this class. We just need to understand that a frequency distribution or doing it by proportion or percent, our bell curve that we're going to rely on, that's what we're talking about when we talk about a distribution of values. I might throw a couple different little shapes to you at the end. Like I'll tell you, instead of looking at this is a normal distribution, we might do like a chi-square distribution, which has a longer tail. It's asymmetric. I might talk about Poisson or some other ones. But for now, we're going to stick with this idea of a normal distribution. Because sometimes distributions are a better way of looking at data than this. This is a mess. This is a scatter plot of a variable, and you can't really see anything in it, right? I mean, it's just a whole range of numbers. Whatever this variable was, I think it's a feeling thermometer. We have a whole range of scores on the feeling thermometer from 0 to 100, and they're just sort of scattered about in here. And can you tell which value of the feeling thermometer between 0 and 100 has the most observations? Okay. When you say kinda,
that one around 70 looks like it has the most.
there's a lot there, right? There's a lot here. But are there more there than there are at the top one? Oh, we don't really know. You're probably right. That's probably the one with the most. I would say the one around 83, that one's got a lot too. But this isn't helpful. This is a way to visualize data, again, completely not helpful. But if we took all 2,300 observations and instead said, let's put them in a distribution that we're used to seeing, well, then we can get a better idea. All right, so one type of distribution that we've talked about, we've mentioned, is a frequency distribution. A frequency distribution is like a table. It's just a list, and it tells us how many times each value occurs in the data set. So how many zeros did we have? How many ones did we have? How many twos did we have? How many threes did we have? Yeah, I told you guys this stuff last class. Right? We were talking about different ways of looking at data. Right? Frequency distribution table, how many times each value occurs. Cumulative frequency, add up the values, get a percentage. So again, nothing new here. Well, here's what one looks like for that data. And you guessed it was the 71, and I said maybe it was the 81. Who was right? I was. Ha! You suck. 440. But you couldn't really tell. 399, 440. Like, that's a lot of dots, right? So this really wasn't the best way to show this data. But this table, really easy and simple way. So the value 399, or excuse me, the value 70 appears 399 times. That is 17.3% of our data. And this column here is the cumulative frequency. It adds it up to 100. All right. I'll get back to this a little later. Think of this when I ask you a question at some point. Okay. These frequency tables are really neat. They're helpful. They're a good thing to have. They get really cool the last half of the course when we have an independent and a dependent variable. So when you want to look at something based upon categories, let's use gender. You'll have a male column and a female column. And let's simplify it. Let's do spanking. That's my example, right? This is known as a crosstab. Again, it's another form of a frequency distribution table. Instead of counting, we're both counting and dividing by another trait. So this is going to be the total number of males. This is going to be the total number of females. Adding down. Adding across, we're going to get the total number of no's. And adding across, we're going to get the total number of yeses. Hopefully these two numbers are the same if we add those together. All right, so that's known as a crosstab. It's another form of a frequency distribution table, and it's actually a lot more interesting. All right, so that's one way we can sort of set up our data. Let's get into the actual measures now. First thing is the mean. Mean is our average value. Mean and average are exactly the same thing. Mean is the more scientific, technical term. Average is what you tell somebody when you want to hurt their feelings, right? Like, yeah, pizza was okay. It was average. It's like the version of fine. How was it? It's fine. Okay. Simple math. The average value, the mean, usually denoted by X with a bar on top. X bar is the sum of all the X's divided by the number of X's. If I want to get really picky, put a little I here. So I'll put a subscript to my subscript. That's if you want to be really, 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 really picky. So again, 6th grade. You take all your numbers, you add them up, you divide it by the number of numbers you just added together. That's your mean. If you have a frequency distribution table instead, well, we can just sort of combine these steps. The f of x. What is f of x? F times x. So we can just add up if we have a table. What's 0 times 124? All right. What's 1 times 1? What's 5 times 3? 8 times 1?
8.
10 times 2? 15 times 99. Fifteen times 100 is 1500 minus the 1. Yeah, that's what I just wrote. Okay. 20 times 4. Somebody say 60. 25 times 3. Look at that. I can just call these all out. We might have to get into fingers and toes a little later, but, right, like 30 times 116. 3 times 16, 330. 30, 48. Yeah, okay. We can go down through the list. Or you can break out your iPhones and use the calculator app. But eventually, once we have all those f of x's figured out, we just sum them together. All right, and we'll get a number. And then we divide by n. Where's n on this table? Yeah, it's the total number, right? Now do you see why these can be handy? Because you can quickly calculate a mean if you have a frequency distribution table instead of just a list of 2,300 numbers. Now let's be honest. There's actually a really even quicker way of doing this. Here's our spanking data again. I forgot to save it, apparently. Here's a great trick in Excel. We'll do, what's the mean of case ID? Case ID is just a count, 1, 2, 3, 4, 5. You want to know what the mean is real quick? Just highlight the numbers you're interested in. And it's right down here at the bottom. Or you could want to report it as a variable. Equals. There's a function called average. Oops. I can never do this in Excel. Equals average. Oh, I think you might have to highlight it. There we go. Whatever. There we go. Well, I was in the wrong cell. Average. How? How can it be 0? Stupid computer. All right. Well, if you're not me, it's that easy in Excel. Stupid computer. You really shouldn't be using Excel anyways, but we'll get to that later. All right. Sum of fx divided by n gives us our mean. You cannot use this on nominal data. Why not? We are dealing with numbers. Nominal data has numbers, but the numbers are what was our example of nominal data? Do you remember? Yes, that is what nominal data is, but do you remember our example? Yeah. Why don't the numbers matter? Yeah, because it's just a way to sort of label a category. So why would you calculate the mean of a number that doesn't matter? It's not going to give you any information you need. So they can't really be used on nominal data. And when I say it's nonsense for a dummy variable, maybe nonsense is a little too strong. It's not really nonsense. It just doesn't give you a mean. It gives you something else instead. How is our dummy variable measured in terms of the numbers? Zeros and ones. So if I take the average of a variable that is just zeros and ones, what am I going to end up with? I will give you that. I will end up with a number that is between 0 and 1. But what will I really truly end up with? It won't be the mean, because mean of a light switch, right? Again, on, off. So if I tell you that the average gender is 0.64, what does 0.64 mean? Let's see, the average male, it's a dummy variable. Come on, somebody, turn your light bulb on. What is that 0.64 number? Yeah, all you get out of this is the proportion of your quality, right? Think about it. You have 100 people, 64 of them are men. 64 times 1 equals 64. 36 of them are women. 36 times 0 is 0. 64 plus 0 is 64. Divided by 100 is 0.64. That's your proportion. 64% of your sample is male. That's not an average. That's not a mean. That's not an average. That's a count, right? That's a frequency. So you're saying that the average value is something that A, doesn't exist, because nobody in the world can be 0.64 male. You can't be, because you're either a 1 or a 0. So it is kind of nonsense, but you do get a value. I mean, mathematically, you get something useful. You just get the proportion of ones. So that's your average for a dummy variable. So this isn't helpful. So when can you use a mean? Well, obviously a continuous variable, something like age, if we want to do the average age in a room. We can also use it on an ordinal variable, because in an ordinal variable, the numbers have meaning, like a student evaluation score. If you have a 5-point scale from excellent to poor, 3 will be fine. Yeah, he's fine. All right. And I get a score of 4.5. Does that 4.5 have meaning? What does it mean? I'm good to excellent, I would argue. Right? I would say I'm between the two categories. Right? I'm better than good, almost excellent. Right in between those two. So means best for continuous data, will work for ordinal data. Nominal data doesn't make any sense. It'll give us a number. It just will be a nonsensical number. Because if Catholics are 3s and Jewish people are 6s, and like you could get a number that doesn't correspond to any category. You're somewhere in between Jewish and Catholic. You're Shinto. It makes no sense, right? And then dummy variables, you get a number, but it's a proportion, and that doesn't always make sense considering dummy variables are either zeros or ones. They're not 0.64s. The book talks about the mean as a balancing point, kind of like this idea. The mean is the point at which every number below it added to every number above it equals out. The sum of the negative differences equals the sum of the positive differences. And we're going to borrow from this idea next week when we talk about a standard deviation. So here's a data set, 9 scores. The mean is 3. How far away is each individual observation from the mean? This is known as x minus x bar. Score x minus the mean, x bar. You get negative numbers, but when you add them all up, -1, -2, -2, that's a -5, +0, +1, +0, +1, +3, that's +5, -5 plus +5, 0. So the differences from the mean, that's something we're going to borrow when we look at variation. How much difference from the mean is there? One more thing about the mean. So I usually call it x bar because we're used to working with samples. But if we had a population, we had all of the data. Let's say we had all 50 states. The mean for that is known as mu. Greek letter mu. And this is one of the confusing things about statistics. And I wish at some point we would all just sit down and go, all right, we're agreed. We're going to use this standard. Right? We're all going to use the metric system. So then when I work on my car, I don't have to have 2 sets of wrenches. That would be nice. I wish mathematicians would get together and say, all right, we're going to use these letters. Because even the x bar you can see in different ways. Textbook sticks with x bar and mu. Mu is a Greek letter. And we use the Greek letters to signify parameters. A parameter is a representation of the population. Sometimes you would say the population mean is, or you have a sample mean of. The letters denote what it is. So if it's a regular letter that we're used to using, can't for the life of me think of the name of our alphabet. Somebody help me out. The English alphabet. We'll go with that. So if it's an English letter, that means it's a sample. If it's a Greek letter, that means it's a population. Just stick this in the back of your head, because you'll see both. We will see both in some of our work when we have the sample mean, but we want to know how close it is to the population mean. Okay, that's mean. It's more than you thought you learned about the mean in 6th grade. Let's go on to median. Median is what we use for the middle observation. So when you're driving down the road, where is the median? It's in the middle of the road. Should you drive across the median? Why not? Why not? Yes, it's illegal, but that's the reason number 2. What's the real reason you shouldn't drive across the median? Why is it dangerous? Okay, because oncoming traffic is coming in the other way across the median. My son John has the hardest time understanding traffic. But Dad, why aren't we going? Because there's cars surrounding us and they're not moving. Why don't you go over there? That's oncoming traffic. They would hit us. So I always have to explain to him like the lines on the road. And I always get to this, the yellow lines. I have to explain to him why you don't cross the yellow lines. And it's because of oncoming traffic. And he just doesn't care because he wants to be home. All right. The median is our dividing line. It splits it in half. So in order to find the median, we have to know what the middle observation is. Because we have our distribution, and we want to know the number where half is on one side and half is on the other. Again, you learned this already. To find the value of the middle observation, you have to identify the middle observation. So you have to know how many observations you have and get a rough approximation to where the midpoint is. So if you have 2,306 observations, you divide that number in 2, and the middle observation, oops, I did that wrong. Why didn't somebody tell me that wasn't odd? Now I've lost my pen. Which is unfortunate when you only have one pen. All right, sorry. Odd number, n plus 1 divided by 2. So this should be an odd number. Will give us 1155 divided by 2, 2.5. Why is that wrong? We'll get to it. All right, so let's look at a data set. How we have 7 observations. The median is the n plus 1. Oh, I forgot the plus 1. That's why. Duh. Jesus, you can be so dumb sometimes. There we go. Still got to erase that. Okay. 2305 plus 1 is 2306 divided by 2 is 1153. Why'd you guys let me get rattled like that? All right. So then we find the 1,153rd observation. And now you're going, crap. That's a very large number to count up to. Well, if we were smart, and we did our frequency distribution table, we just got to add these numbers up until we get to 1153, right? All right, let's get started. What's 124 plus 1? All right, plus 3. Let's see how long we can take this, Hampton. Plus 1? Plus 2?
130.
Plus 99? That's all right. It's 230. Let's stop there because we've gone, what, 5 numbers and we've already made a very simple mistake. How are we going to find the median point in this distribution? Looking at this table. It's in the middle. You got that. So I take my hand out and go, okay, I got 1 hand and 2 hands and 3 hands up. What am I going to do? You're going to say that this is the median value. You're not. Why aren't you? You think it's right here. It's not. You're wrong. You're really, really wrong, right?
Yeah, I was thinking it's the other total.
What other total?
Isn't it, I don't know.
Where's the value for the 50th percentile, the middle? How can I find where there's half below and half above? You could if you want to take a really, 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 really long time. What total? That's to tell us which observation is the median, but how do I know what the value of that observation is?
You take the value of 65 and subtract the value of 70.
No. You're close, though. Why did you pick on those 2 numbers?
Because the 50th percentile is in between 65 and 70.
No, it's not. Okay, you've keyed on that last column, which is the cumulative frequency, right? So we start at 0% and we're working our way all the way up to 100%. To get to the value of 65 has all the way up to 48.05%. So it stops there. It stops at 48.05. 70 contains 48.06 all the way up to 65.35. So that 50th percentile, that middle percentage, is in that long string of 70s. Does that make sense? I just need one person to tell me it doesn't make sense. That's all you need. Just one. One person, be brave and say, I have no idea what you're talking about. Because I got one more way to show this. All right. So distribution of numbers, right? We're going to start at 0, and we're going to go to 100. Got that? Okay. This number here, this cumulative percentage number, tells us how far on the path to 100% we're going. So 0 takes up 5%. 1 takes up another 5%. 5 takes up another 5%. So how much of that little curve have we filled up? Right, because the cumulative percentage, oh crap, sorry. See, I'm much better with you guys because I screw this all up on the Tuesdays. I'm like, this is great. This will work. Okay, so we start at 0. The 0 is this number here. It's 5%. 1s is how much? Yeah, like nothing. Like I'm not even going to... The 3, the 5. Is it how much more? I can keep doing this. The 8 is 0.04. The 10 is 0.09. Finally, we get to the 15. That's another 5%, right? So now at 15, I've now covered about 10% of my progress to 100%. Let's skip all the way out to 30. 30 is another 5%. And I should be up to a total of 15%. Now are we okay? Now that I actually have gotten this right? Don't ever come to the Tuesday class. It's this bad. Okay. Well, if I keep doing that, and I had a sense of proportion, what number am I going to have to hit that 50th percentile? Well, I'm going to cross over it once I start coloring in my 70s. Now does it make sense?
So, like, how do you know where the exact 50th percentile is? If it's like, you know what I mean?
How do I know where it is?
Well, I know it's in the
Because I
70s.
know it's in between that range of values.
So you just know where the range is.
Well, let's think about it, right? So if I did this, right, and I did it right, and I went all the way up to 65, and I kept adding these numbers together, I'm going to get to 48.05. Have I crossed 50 yet? So I'm going to start adding these 70s in. Now remember, in our data set, we have a string of 400 70s. As I keep adding these 70s in and I get closer and closer and closer, it's going to be a 70 when I hit that 50% point. Does that make sense? Okay. If it's an even number, like this data set actually is, you have to take the average of the two numbers in between. So the 2306 divided by 2 plus 2306 plus, well, divided by 2 plus 1. So this is going to be the 1153 and the 1154th observation divided by 2. Again, we have a very long list of numbers. Chances are these two numbers are going to be in the same category. And that's why I can, again, do the same thing, which is look at my frequency distribution table. You are virtually never going to get a number to end at 50. You're just not. Right? Because if you have a category, even if it's 5 categories, even if it's 2 categories, you're going to end up with something that is more than the other. So what you're looking for is you're thinking, okay, I have my frequency distribution table. 65, has that number crossed 50% yet? No. 70, has that number crossed 50%? Yes. That means 50% is in this number. In this 70, it's among the 17.3%.
So how is the number that we get from the median formula, how is that helpful for you to scale with the PQA?
Exactly. I'll tell you when it's helpful. When you have this. This is when that formula is helpful, right? When you don't need to do a frequency distribution table because you've got 2,300 variables, or 2,300 observations. Here we have an example, okay? We have 7 numbers. What's the median number? Well, okay, n equals 7. 7 is an odd number. I take my 7, add 1 to it. That is 8. Divide that by 2. It's the 4th observation. So which one is the 4th observation? Nobody wants to say 0? There's 0. There's 1. There's a 2. There's a 3. There's a 4. There's a 5. There's no 6. There's no 7. There's 1 8. That's all my numbers. 1, 2, 3. My 4th observation. I want somebody to say 0 because they just counted over and they're like, hey, the 4th one's 0, which makes absolutely no sense because it's the lowest value. You have to reorder the numbers, right? You have to put them in consecutive order. Why? Well, again, let's think about this. Our data is a distribution. This one is flat as hell. So actually, I can't even make it look like a curve, right? It's just 0, 1, 2, 3, 4, 5, 8. Like, that's not really much of a distribution because it's really, really flat. It also ends here, 0 to 8. So where's the midpoint of this? Well, the midpoint of it is at 3. 1, 2, 3. There's the center of our really flat distribution. Again, I can't draw worth crap, so. It would take you longer to create the frequency distribution table for this number than it would be to just do that. Here's another one. 15, 24, 39, 31, 42, 19. Okay. I have 6 observations. Should we reorder them first?
Yes.
Okay. Which the first one?
15,
Then,
19,
then,
24,
then,
31,
then,
39,
then.
42.
42, 39, 31, 24, 19, 15. All right. Do you even have to do the math? So, right? 6 numbers, you can just look at it. Which of these 6 numbers, which are the middle 2? Okay, so 24 and 31. Our median is going to be in between 24 and 31. The n divided by 2th score, so again, 6 divided by 2 is 3. The 3rd score plus the 3rd plus 1, which is the 4th score, divided by 2. Yeah. That's our median value. But the median value doesn't appear in this data set. All right. So that's median. Again, you should be having a flashback. I got no fancy tricks for the median other than that frequency distribution table. A lot of times you can just find it by looking for the cumulative 50th percentile. Last measure of central tendency is the mode. I don't have an equation for the mode. I can make one, like the absolute value of the frequency of, we don't need an equation for it. The mode is just the most frequent value observed. I'm pretty sure the only reason we have the mode is for when we have data that doesn't fit to a traditional idea of a distribution. And that's nominal data. Again, because the numbers attached to the value labels, Shinto, Christian, Jewish, completely made up and don't matter. So that's why when you have data like a name, well, the best representation of that name is just the one that appears the most. So what do you do to find the mode? You look for the largest number on the frequency distribution table. I've got one of those. What's the largest number on this frequency distribution table? 80 what? 85. 440 of them. So here I'm looking for the median. Here I'm looking for the mode. Okay. I want to do that. Here's another one. Our good old friend, the bar chart, which again, you're not allowed to make, really. Like you can use it as a tool, but you can't use it to actually give me any information. You can make it to solve a question, like which one's the mode? Well, which one has the highest debt? The UK. Has the highest bar. Congratulations. Intro to stats, you now have statistics. No. Can you tell me why it's wrong? All right, we can look at it. What do you want to see about this one?
No, not that one, before.
Okay.
No, you're good. Keep going.
Oh, even better.
Okay.
Oh, your slide copier. All right.
Yeah.
The one that has the most numbers, the most dots, the highest bar, whatever. Whatever you use to denote frequency, the highest one, whether it's a number, a bar, a dot, line, whatever. Highest one, that's the mode. Thank you. Okay. So now we have statistics. Here's the thing about statistics, and this is why people say, oh, you can lie with statistics. Yeah, you kind of can. But the reason is when you use statistics for something that it shouldn't be used on. You should not use the mean on a dummy variable. You shouldn't use the mean on a variable that's nominal. So depending upon your variable type, the mean, the median, or the mode might be the most useful one to use. These three methods are all measures of central tendency. So they're all there to take a data set and describe it down to a common value. But they each have their strengths and their weaknesses. Mode's great. Why is the mode great? Well, it's easy. It works on nominal data. When you think about it, the mode is an actual value. It's not a 4.5 like with our ordinal scale, where I have to say, well, I'm between good and excellent. The mode is an actual value. Think of a distribution of student evaluations where lots of people love me, and I get almost all excellence. But in one class, there's that every student that just hates you. And he gives me a fair or a poor. What's that person going to do to my average? It's going to bring it down. So I can have 15 excellence and 1 poor. Now what's the best one to represent how my students love me? The mode, right? Because 15 out of 16. 15 is my highest category. And this is where statistics gets a little shady, right? Because really, is the mode the best way to represent ordinal data? No, but it can, right? I can get an answer that can represent that data. It's not the best one, but it's one. And so I can say at the end of the year, well, you know, the modal value of my student evaluation scores was 15. Therefore, my students think I'm excellent. Except for that one person. Don't be that one person, by the way. All right. Mode allows for multiple modes. We don't really care about that. And here's the other one. The mode is not affected by outliers. That one person that gave me the poor, that gave me the lowest score, that's the outlier. The mean, well, my mean was pulled down by that outlier. But it doesn't affect the mode, which is why I chose it for this example. The problem with the modes, well, it doesn't really represent the entire distribution of the scores. Same example, student evaluations, class of 15. Let's say I'm really sexist, instead of just a little sexist. And I get a distribution like this. The 8 guys in the class think I'm awesome. The 7 women in the class hate me. You notice how I draw it out, that hate? Like, not just hate, like hate me. Okay, just want to make sure you're paying attention. I got 8 excellence from my guys and 7 poors from my insert derogatory term here. If I say, well, my teaching in this class was excellent, my modal response was an 8, I'm ignoring that pretty much other gigantic part of the distribution. I'm ignoring all of those 7s. Okay? Those 7s aren't an outlier. An outlier is the one random observation that's out there. Like that one guy that just didn't get me. Thought I was picking on him when I was having fun. This situation is a lot more sinister, right? Because I'm basically just saying, well, those 7 didn't exist, which is like 40-something% of my observations. I'm not even counting them in. Okay. Because of that, we can't use this in hypothesis testing. because it doesn't represent the entire distribution. And when we get to hypothesis testing, you have to absolutely 100% work with a distribution. Because if you don't have an entire distribution, you can't do hypothesis testing. Does that make sense? Taylor? Okay. Median. Median's good for when you have a skewed distribution. So when your distribution is asymmetric. Again, a distribution becomes asymmetric or skewed in the presence of outliers, because an outlier just pulls that tail, right? Pulls the tail out. You might get more observations on one end. The problem with the median is it really only relies on one or two scores. So a very similar problem to our mode. Our mode relies upon the most frequent score. Really, the median only relies on the one or the average of the two in the middle. So again, our distribution of scores, if we're not looking at the entire distribution of scores and using that in the calculation, can't do hypothesis testing. The other problem with the median is that the median doesn't do well with bimodal distributions. So again, you have a distribution with lots of likes and lots of dislikes. But let's say I have one student that's like, he's okay. So I have 7 that love me, 7 that hate me, and I got 1 in the middle. Oh, my median score is okay. That hides the fact that they both love me and hate me. So I'm basing my categorization, my label, off of the one student in the middle. All right. So mean we really like so far, because the other two I've said you can't do hypothesis testing. Great thing about the mean, you use every single observation. Every single one of them. From the first to the last. And because you use the entire distribution, yay, we can do hypothesis testing. The weaknesses, I don't care about, because I'm really happy that I can now do hypothesis testing. Because science, remember, we're here to learn about statistics so that we can do science. Yeah, the mean is affected by outliers. Right? That one poor student's going to drag me down. But let's be honest, it's just a little bit. As long as I got 15 people that love me, I can have one hater. It's okay. So I'll be 4.7 instead of 5. Whatever. I'm really high. Right? Close to 5. And it doesn't do well with bimodal distributions. So again, half that like me, half that hate me, they're going to tend to cancel each other out. So if I have 8 5s and 7 1s, 8 times 5 is 40, and 7 divided by 15, I'm going to end up with like a 3.1 something average. Not the best to describe my bimodal distribution, right? I might not even know that it's bimodal. If I just calculate the mean and I don't look at the distribution, I could just think I'm average and not the fact that I'm polarizing. Well, I'm a either you love me or hate me kind of guy. Right? Or just everybody thinks I'm normal. Everybody thinks I'm average. Like, yeah, Woody's okay. Yeah. He's there. Everybody gets a B. They don't really care. Yeah, he's okay. I passed his class. All right. So mean we like. It's not perfect, but it's a lot better than the median and the mode. If we're lucky and our data is normal-ish, the mean, the median, and the mode should all be the same thing. That's the best case scenario. Because our most frequent, our highest point, happens to be in the middle. And if we have equal amounts on both sides, they'll cancel out, and that's our mean point. That's great. If we're asymmetric, if we have more at an extreme, well, then it's going to reorder our mean, our median, and our mode. Our mode's always going to be the highest point. The mean is always going to be towards the skew, and then the median will be in the middle, because that's where the median is. Median's always in the middle. It might not be today, but at some point, this idea of thinking of data in a distribution like this, rather than in an Excel file or a frequency distribution table, is going to be really important. Because in the best scenarios, our data is huge, like hundreds, thousands of observations. And that really doesn't fit well with the table. We have to start thinking about it in the larger picture, right? And the idea of our data as a distribution, regardless of the shape. I'm not really too concerned about the shape right now. But the idea that you have a minimum and a maximum, and you go between those two values, and that the one that you see most frequently, the mode, is the highest point in the distribution. Like, once you can start thinking of data that way too, this is going to go a lot smoother. Bimodal, again, we talked about this. I can have two groups, love and hate, but if I stick to the median and the mean, I'm going to find the midpoint. It's not going to be very descriptive. Okay. Yeah. We okay with this? Okay, I want to show you one more thing before you leave. All right. And I want to know why it wasn't in my slideshow. All right. I'm going to go back to the SDA website. Okay, let's pick something. Let's talk about women in the armed forces. Why don't they have just general combat? Am I missing that one? Here we go. Fee fight. Let's take a look at this one. Okay, dummy variable. Not going to be too helpful. As far as you know, are women now assigned to jobs in the armed forces should expose them to combat, or are women not assigned to such jobs? This isn't even an opinion question. This is a general knowledge question. Do we know whether or not women are in combat right now? I go. Do you know?
Aren't they not right now? But it's two.
Yeah, we're working on it. Trying to figure out which classifications are okay. We have some that are okay right now, namely pilots. They're okay. But whether it's actual infantry, the Marines are working on the actual kind of like getting infantry together. All right. So this is a knowledge question. We don't know whether or not what the answer is. I don't even know what year this was done, so this was a bad one to pick. Again, this is what happens in the Tuesday class that you guys don't usually see. Let's find a different variable. Happiness. I want to do happy. Give me a scale. All right, I got a scale of 3. Taken all together, how would you say things are these days? Would you say that you're very happy, pretty happy, or not too happy? %, not too happy. Life sucks. 2%, or 2, pretty happy. Things are okay. 1, very happy. Everything is awesome. Where's the median? 1, 2, or 3? Why? That's not the median. I said median, right?
Yeah.
Where is the median? 1, 2, or 3?
It would be.
I'm not going to hit you if you get it wrong. Just guess.
I think it's still in two.
It is still in 2. How do you know it's still in 2?
Because there's over 50% of the data is in two. So you take the 12 from earlier to 31 off.
You got the right answer, but for the wrong reason. Again, I want you to start thinking about data in terms of the shape of the distribution. So I'm going to, let's bring this with us. No, not that new one. I want this new one. Here, give me a new one. Well, it used to be Control M. Delete this. Okay, so here's my data. Okay, how do I know that my median is a 2? If we start thinking about data as a distribution, and we start at the lowest value, which we're not too happy. That's low. I don't care if it says a 3 or not. That's pretty low, right? You're not too happy. What percentage of it is not too happy? Okay. My next is 2. What percentage of my data is is pretty happy? And what percentage of my data is very annoyingly happy? Okay. Now, let's see, this side over here is probably a little bit more skewed out because it's a higher percentage. Now, how do I know where my median is? My median is the middle. Where's the middle of my distribution? In the 2. Okay? So if I think about it this way, right? And again, this is what I want you to start thinking about data in terms of its distribution. All right? If we have a normal curve, that's always going to be an assumption, but let's just assume it anyways, make my life easier. Draw out the normal curve. Think about, all right, this data is represented by this curve. How much of the curve is my 1, my 2, my 3? These guys should have coded this wrong. Because if your variable is about happiness, this should be your highest value. As your values go up, you get more of your quantity. That's the way they should have coded it. Not happy. Yeah, things okay. Life is awesome. All right. I'm going to keep this. The other way you could have done it, well, I'm looking for 50%. If I start at 12, the next one is another 52%. Sorry, 55%. So that's going to take me to a cumulative percentage of 67.68.6. There's the category that my 50 is going to be found in. Okay. I can calculate a mean from this. I can take this table and turn it into a frequency distribution table. So I have 1s times 18,000 times. I have 2s times 32,000 times, and I have 3s times 7,000 times. If I want to find the average.